if I do it, if I share it this way instead. If I just do this, does this look like higher res to you? It does, right? I'm losing my mind. This looks higher resolution, right, than the other way I was sharing it? I think so too. Okay, I'm gonna look at these two. I was trying to do the share where I can see the like presenter thing of the clock.
Oh,
But I think if I do it without that,
is the clock over there? I probably don't use.
it's okay. I also have a watch that I can just.
Okay. Okay. I can also tell you.
Oh yeah, that would be helpful.
That's 4. That you know it's 4. Or
Oh, when the hour is done. 10 minutes before would be. Tell me by getting up and leaving.
Oh,
Hey, good. How are you? It is, isn't it? Sorry for the shuffle.
Oh, no, that's fine. I actually am not going to tomorrow.
Oh, sorry.
I have, no, I'm free during your block period. Maybe.
Yeah.
I am, yeah, luckily your reputation, so I need to know no more.
Oh, great. Yeah. For what, sorry? Oh, perfect. Yeah. Yeah. Great. All of July?
No, not like a week. Where do you live in San Francisco?
I live in like faculty housing apartment right next to campus. So yeah. That's what we're affording right now.
Well, yeah.
Yeah. Yeah. You know how that journey goes.
One of my sons moved to Palo Alto, he said, you gotta live in East Palo Alto, that's where it's cheap.
Yeah, that's right. That's right. Yeah.
It's not nice, but it's.
Yeah.
It's have to figure out do you want the absolute value of the when I first started, I was like 4 months, and 4 years, and the faculty housing is great. And then when I left market, I was like, oh, the delta
Yes.
dollars has gone up by significant, but still.
Yeah. And I have the same, I think, similar deal to you. Like we can only stay in this place for 5 years and then time to figure out something else.
Why are we?
Yeah, right, exactly. Too real, Bay Area.
Someone made it, and I saw it, like, oh, wow. Like, oh, wow.
it's only 1 minute past.
Well,
Ended already, so.
I mean, that's Fox reputation, best Fox reputation.
Yeah, I'll give it 30 more seconds.
Oh, it's far away. Oh, it's
Should we start? Okay. So it's my great pleasure to introduce our seminar speaker for today, Professor Susan Clark. She did her undergrad in physics at the University of North Carolina on Chapel Hill, and then her PhD at Columbia University with a thesis titled Magnetic Fields in Interstellar Mediums.
Yes.
And then Hubble Fellowship at IIS, and is now faculty at Stanford University. And she's an expert on physics of the ISM, as well as galactic magnetic fields and other topics. And please join me in welcoming her to our seminar to hear from her awesome expertise.
Thank you so much, Joanna. And thank you so much for having me. Can everyone hear me okay also on Zoom with this mic? Okay, perfect. Yeah, it's such a pleasure to be back at CITA. I haven't been here since the pre-pandemic years at this point, and it's really wonderful. I've already had a full morning of chatting with many of you and really looking forward to more discussions about all the exciting things people are working on. So I've packed this talk a little full of exciting things that we are working on, broadly centered around themes of using morphological information from our probes of the interstellar medium to learn things about magnetic fields in the interstellar medium and also the phase distribution of the ISM. So the work I'm going to tell you about today is done with many people, some of whom are in my nascent group now at Stanford, where I've been for about 1.5 years now. So I've called it the Cosmic Magnetism and Interstellar Physics Group because I could not possibly come up with something more concise. But I won't do any justice to the variety of things that people are working on. And I would like you to be seeing their faces on the screen right now, but it has advanced here and not there. So let me try again. Sorry about this. See my screen, right? Okay, now it's working. Right, so I won't do any justice to the variety of things that people are working on, but I want to flash the wonderful faces of the people at Stanford who are involved in this work, as well as many collaborators elsewhere. You all, I hope, appreciate that magnetic fields are absolutely ubiquitous in our universe. And today I'm going to mostly be talking about the magnetic fields within galaxies, specifically our own Milky Way galaxy, on scales relevant to the physics of the interstellar medium. And really, no matter what problem you like to focus on in your own research, you probably know, at least deep down in your heart of hearts, that you really can't or shouldn't be ignoring the role of the magnetic field, right? They affect a huge number of physical processes in direct and indirect and still very unknown ways. And so if you care about star formation or structure formation in the ISM, if you care about understanding turbulence in interstellar environments, if you care about the propagation of cosmic rays and how they might influence other physics of the universe, you really need to be worrying about the structure and the strength and the distribution of magnetic fields in our universe, and on a variety of different physical scales and different environments. So one possible motivation of this whole line of study is that the interstellar medium is a very rich, complex physical system where gas is transitioning between just a bewildering array of physical states, right? From very hot, very tenuous plasma, all the way down to very cold, dense molecular clouds, where, as we know, eventually stars are able to form out of the ISM. And those stars live out their lives interacting with the ISM and feeding back energy and momentum into the system. Some of them explosively contribute their matter back into the ISM. Others carry pockets of the ISM away with them forever. But we need to understand how this whole process is happening, and on many different pieces of a simple diagram like this, one of the most poorly understood aspects of what's going on is the influence of the magnetic field. And then the slightly more technical way that I like to motivate studying ISM physics is that we get to, and we have to, care about this range of physics over a huge range of physical scales. And again, at many different physical scales in this system, it's the magnetic field that is one of the most poorly understood components of the story. So the good news for our study, it's complicated, it's rich physically, but we also have observational probes that let us get a handle on the strength and structure of magnetic fields in the ISM. We can, and many of you here do, study Faraday rotation, right? This rotation of the linear polarization angle of light as it passes through a magnetoionic medium. We can measure synchrotron radiation from charged particles accelerated in magnetic fields. And then most importantly, for some of the work I'll tell you about today, we can measure magnetic fields in 2 different ways, thanks to the presence of interstellar dust. So the ISM has lots of dust in it. The dust grains, these sub-micron scale chunks of matter, are on average not perfect spheres. They are somehow elongated little American football shapes you can think of. And they find a preferred orientation with respect to the ambient magnetic field that they sit in that has 2 very helpful consequences for us, right? These little magnetically aligned dust grains preferentially absorb one component of the polarization of initially usually unpolarized background starlight. So if you measure linear polarization of starlight in the optical or near infrared, you measure an imprint of the magnetic field orientation in the dust between your telescope and the star. And then these dust grains are also thermally re-radiating emission. And so if you measure the linear polarization of the thermal emission of the dust, it is also partially polarized, also in a way that gives you this imprint of the magnetic field orientation. So we have all of these different observational probes. Surely this is the easiest problem of all time. Look at all these different ways we have to tackle it. But of course, what that obscures a little bit is that each of these probes is sensitive in general to only a single component of the 3-dimensional magnetic field. So either the component along the line of sight or the component projected onto the plane of sky, typically. And also to different phases of this very rich multi-phase ISM that we also need to understand in some detail. And so putting all of this together into a complete picture of how the magnetic field is influencing any particular region or process, this is a significantly difficult problem to tackle. And in case you want just one more motivation, in case you're thinking, well, I'm safe from this because I am a cosmologist and I don't care about the ISM or star formation or what have you, this beautiful image of polarized thermal dust emission that lets us trace this imprint of the magnetic field from this polarized thermal dust emission to you, cosmologists that I have invented in the audience, might look more terrifying than it looks to me, right? You can think of this as either a great way to measure magnetic fields in the neutral ISM, or you think of this as a horrifying, very bright, very polarized foreground to very faint polarization signals that you might want to be detecting at these sort of microwave frequencies. And so your final motivation for this work, just to make sure everyone's excited, is, as I'm sure will be familiar to many of you, that if we want to make excellent measurements of the polarization of the cosmic microwave background, and in particular, if we want to detect this primordial B-mode polarization signature in the CMB, we need to have a very thorough understanding of this bright polarized thermal dust emission from the Milky Way. This is our age-old saying that one person's treasure is another person's foreground. I like to position myself as an optimist in this scenario. We need to understand actually both this very bright dust polarization from the Milky Way and also the synchrotron, the polarized synchrotron emission from the Milky Way as well. But what that means is that we are building these phenomenal experiments to measure the polarized CMB that are also making really deep, wonderful measurements of magnetic fields, the interaction of matter with magnetic fields in our own Milky Way. And so your final motivation here is that the better we can understand the structure of the magnetic ISM, the better we can remove it for you if you'd like to get to some faint underlying signals in the cosmic microwave background, and vice versa, right? The better that we can make measurements of this emission, the more we can learn about the magnetic ISM. And so my story for you today is focused on the fact that in the ISM, we have a really spectacular range of spatially resolved observations of emission of many different components of the ISM. And that spatially and sometimes also spectrally resolved data means that there is a very rich morphology that we are able to see with our eyes when we look at our different ISM tracers. And if we can capture that information in quantitative ways, we can ask new questions of our data that let us learn new things. In other words, there's very rich physical information in the spatial distribution of ISM tracers that we would like to use. This is in particular highlighting the fact that on many different scales and in many different tracers, we see filamentary structure in the ISM. And this is a important ingredient, we think, to how star formation proceeds out of the very first phases of the ISM down to the core scale. And in particular today, I want to talk about how we can harness morphological information encoded in the 21 centimeter line emission from neutral hydrogen. So this halting video is attempting to show you. This is the spin flip transition of neutral hydrogen, so 21 centimeters. This is data from the Galactic Arecibo L-band feed array H1 survey. So this is 4 arc-minute spatial resolution across the whole sky visible from Puerto Rico, from the site of the Arecibo. That means that the bottom of your screen here is about -1 dec. The top of your screen is about +38. All right ascensions are panning across the screen. And the movie, you can maybe see a little bit, is also moving back and forth along the line of sight in Doppler shifted velocity, right, in frequency space. And so the beauty of the 21 centimeter line for a lot of what I want to tell you about today is that in addition to this spatially resolved structure, we also have velocity information. We have some information about what's going on along the line of sight from just the Doppler shifted line. Is this all making sense? Please, by the way, feel free to interrupt me with questions anytime. And so I wanted to convince you today that there is information in these data, in the morphology of these data, about both the structure of the magnetic field in the ISM and also the distribution of phase, the H1 phase structure in the ISM. And the goal here is to come up with some sort of quantitative morphological descriptors that actually let us probe how that morphology might be related to the physics of the ISM, and specifically to the multi-phase and magnetic properties of the ISM. So I'm going to start somewhat at the beginning and talk first about how it is that emission structure I just showed you is related to the structure of the interstellar magnetic field that gas is sitting in. And the first way that I went about this, what seems like absolutely ages ago now, is to write an algorithm based on a Huff transform that computes linearity in image space. So I am partially throwing this slide up because I learned today that your very own Ashley Stock is using this for fantastic scintillometry things that have nothing to do with what I'm telling you really. But this was a way to quantify the orientation of linear structures in this neutral hydrogen emission. There's the physics I'm about to tell you about isn't unique to using this particular algorithm. The point is that you can use this to measure the orientation of linear structures. And so what you can do is come up with an algorithm like that, measure the orientation of these anything that is linear in across your entire image in the H1 emission. And that's what's visualized here in the sort of background brushstroke pattern of the top panel. These swirls are the orientation of linear structures in neutral hydrogen emission, okay? And then what you can do quantitatively, in addition to in this pretty picture, is compare the orientation of that H1 structure to the magnetic field orientation on the plane of sky that we infer from the thermal dust polarization. That is the swirly pattern in orange. Yes.
Will you explain to us how averaging along the line of sight so lets you do say characteristics?
I absolutely am going to do that. Here, I am computing this linear orientation in successive velocity channels along the line of sight. So sorry? I am then making just a vector sum along the line of sight. Yeah. And I'll explain why that makes some sense in a minute. Yeah.
Is the velocity or is it like the not velocity over psi now?
So this is all high galactic latitude. I don't know if you can really see, but this exactly, yeah. So you start here about 30 degrees off the plane. Yeah. Otherwise, it'd be cool to make a correction for that, but this won't work necessarily that well in the plane. Yeah, there you go. Yeah, so your galactic North Pole is right off the screen here. Yeah, perfect. Excellent. Oh, and the one other thing to say about this image is that what these little white sprinkles are. Does anyone have a guess? Starlight. Yeah, exactly. Well, it's written right there. But you would have gotten it anyway. Exactly. So that's probing this largely the same magnetic field, except now in wherever the dust is between us and the star, which has a lot of promise for what we can do as we get more starlight polarization measurements. So to the question of how to treat the line of sight property of this, I want to think of that problem in analogy to how we think of dust polarization summing along the line of sight, right? So here is my little cartoon of what is going on in the dust polarization along the line of sight. Here is your distance axis, and here are a bunch of little dusty regions somewhere along the distance axis. To the extent that these dusty regions are sitting in similarly oriented magnetic fields, all else being equal, that sight line will tend to have a higher fractional polarization measured in the dust emission, right? Whereas if the magnetic field orientation is very disordered along the line of sight and distance, you will have line of sight depolarization of that signal, and you will on average measure a lower fractional polarization in the dust. So you might think, what if I just swap distance for what I can actually measure in the H1 data, which is this Doppler shifted velocity with respect to the local standard of rest? Now, I am definitely not saying here that there is a one-to-one mapping between velocity and distance. There is not, right? Especially not at these high galactic latitudes where you can't even lean on a rotation curve for your model. I am simply saying that you might think that if my H1 orientation is physically, locally aligned with the magnetic field that it's sitting in, then maybe sight lines where the H1 emission in many different velocity channels along the line of sight is very uniformly oriented. Maybe those sight lines correspond to places where the dust polarization has a higher fractional polarization. And maybe if my H1 is very disordered along the line of sight, maybe that is also, even though I don't know where it's happening in distance, a sight line that will be depolarized by measurement of the dust polarization. And so you can come up with a way to quantify the order or disorder of the H1 orientation. That's what's plotted on the y-axis here. It is mathematically what is plotted on the y-axis is how you would compute a polarization fraction out of, say, a simulation of dust polarization, out of the sums of vector sum of Q and U along your line of sight. And then you can compare that to the measured polarization fraction in the Planck data at 353 gigahertz. And it turns out these things are actually correlated with one another, which led myself and Brandon Hensley a few years ago to put these pieces together into a model that we described as a model of the dust polarization based on the idea that H1 can trace magnetically coherent regions of the ISM. And really, as far as models go, this is better described as just basically a mapping, because we're just taking the distribution of H1 emission and mapping it into what we call velocity orientation space. And so this is my visualization of velocity orientation space. Velocity increases radially in the red, increases to larger negative velocity in the blue. That is just a visual choice so that the local standard of rest is always at the center of these images. And then azimuthally in each of these hemispheres, I'm plotting the orientation of the linear structures in H1, quantified with this, well, with whatever algorithm you want, in this case, the RHT. The idea here is that if physically, in real distance space, you have clouds of dust that are sitting in differently oriented magnetic fields along the line of sight, and that are associated with H1 at different line of sight velocities, those will naturally separate in velocity space, of course, but also in orientation space. And so to the extent that these are magnetically coherent, we'll see different regions of this velocity orientation space populated by our distribution of H1, just mapped there from the data. And so this is what this looks like if you just take a sight line and you just map the distribution of H1 in velocity and orientation space along that sight line. So clouds is a bit of a misnomer. You can think of this as magnetically coherent dusty structures, but traced entirely from our quantification of the morphology of H1 emission and its intensity as well. And yeah, please.
Some angular scale.
Yes.
To identify orientation. Is that important at all? I mean, it sounds like.
Yes. Well, yes and no, actually. For the basic question of is this well correlated with the dust polarization angle, it's fairly insensitive what you choose. But in more detail than that, we are exploring, and I will get to this a little later, but there's potentially a lot of extra information in exactly how you're doing this mapping, what correlates the best with the dust polarization. And so this first model that Brandon and I built is based on my earlier work, just showing, hey, if you take the highest resolution H1 you can get your hands on, and you measure these orientations on scales of a little more than a degree, this works well. And so that's what we did. Now, one of my grad students is really exploring the parameter space, and potentially we can learn a lot more about actually what is it morphologically that's most predictive for the dust polarization. So yeah, it's a great question. And it turns out that this mapping sort of behaves the way that you would expect, right? So if I take a sight line that has a higher fractional polarization measured in the dust, that tends to have more collimated H1 orientation, even when it's distributed across velocity space. And conversely, if I take a low fractional polarization sightline, you tend to have more disparate regions of this velocity orientation space populated. And I promise I didn't just cherry pick the 2 pixels where this works. This is a statistical trend as a function of the dust polarization fraction that we see. And so once you've made this mapping, once you've just taken your hyperspectral H1 cube and mapped it into your velocity orientation space, you're just a little geometric decomposition away from having a Q and U are 2 Stokes parameters of linear polarization defined purely from the orientation of H1 and its distribution in velocity space. And you can weight that also by the local H1 intensity if your hypothesis is that H1 intensity is correlated with the dust emission, which is a very reasonable thing to think. And what that means is that if I take any slice of the sky here, now instead of, or in comparison to measuring the dust polarization in the two-dimensional view that we are always stuck with if you're making a broadband measurement of the thermal dust emission, now we have this H1 based Q and U that we can compute as a function of velocity. And so this gives us a purely morphology based tool to ask new questions of our data, which is the goal of this talk. You can of course also sum that H1 based Q and U along the velocity axis in direct analogy to the sum along the line of sight of the dust emission, right? And then compare directly what you have created out of the H1 morphology to what you measured in the sky at 353 gigahertz in the Planck data. And so the left here, purely H1 morphology based model, we have taught this nothing about a dust SED or anything like that. This is just pure morphology, and then we can compare that to the dust polarization measurements. And you know, the first surprising perhaps thing is that by eye, these things look like one another, and statistically they are well correlated, especially on larger angular scales. But now you can ask me, okay, great, you've made this strange thing. How can we use this besides just what we've already learned, right? Which is that this H1 morphology is extremely well correlated with the dust polarization angle and with apparently what is dominating some of the structure we see in the dust polarization fraction from this morphological disorder either along the line of sight or in the plane sky. Okay, what else can we learn? And my answer to that is that, well, one, whatever you want, because we have made these maps public, so have at it. And two, that we can learn quite a bit now from two different approaches. One, from comparing our H1 based maps to the real measurements of the sky in order to tease out what physics we think is driving properties, measured properties of the polarized dust emission. And two, we can use the fact that we have now this 3D idea of what is happening along the line of sight to ask new questions about the 3D structure of the ISM. Yes.
How do you define the polarization angles on the sky?
Sorry, how did I define the angle on the sky? Oh, yes. Okay, this is shown in the IAU convention for, yes, there are two conventions to keep track of always here. One is whether you are talking about the polarization angle or the magnetic field orientation, which is orthogonal to that, right? And then the other is what you are measuring the angle relative to. And so I like to use the IAU convention. Be warned that that is a sign of U away from the typical cosmological convention.
But which direction does the magnetic field basically in these two?
So I think this is the magnetic field orientation here. So this is probably the easiest panel to look at. So you've got Q, you've got U.
I'm still not sure what data is. Sorry.
So it should be increasing east from north. Yes, I believe. And I believe this is the magnetic field orientation, not polarization angle. So, okay. In the plane, the magnetic field is oriented along parallel to the galactic plane. Yes, that is a good. All right. And here, by the way, this is the polarization fraction. Here, no air quotes are needed. Here, polarization fraction, but computed purely from this H1 morphology, right? So say, for example, you had just seen this measurement of the polarization fraction over the sky with Planck, and you had thought to yourself, wow, the dust polarization must be really variable in its intrinsic polarizing efficiency, right? Maybe some of these dust grains are really well aligned, maybe in other regions of the ISM they're not. To the extent that these things are well correlated, that can't be what's going on, right? This is purely morphology based. And so that is a good example of how comparing to something that is constructed just from this morphology to ask questions like that. And here are some other examples. So we also know from our measurements of the dust polarization that there are a few sort of standard statistical properties to measure. The dust total intensity is always positively, or for the most part, always positively correlated with the E mode component of the dust polarization. This is this positive TE signal that we see in the dust dominated frequencies of the Planck data. And there also nearly always tends to be this, or well, always on large angular scales over large regions of sky, there is always an excess of the E mode component of the dust polarization with respect to the B mode component of the dust polarization. Just very briefly, the E mode component is the one that is parity even with respect to the Fourier wave vector. The B mode component is parity odd. And we broadly reproduce both of these, this positive TE and this positive EB ratio, or this greater than 1 EB ratio, with these H1 based methods, because both of those in the dust are originating from this preferential alignment of the magnetic field with the sky projected density structures that we see in the dust total intensity. Okay. And so this is in some ways baked into our model by virtue of the fact that we are getting our magnetic field orientation from the orientation of structure. So it is aligned by definition, right? And so we also see, for example, well, here expressed as B over E, and we see that that ratio is less than 1. We can advance to the next slide. Yes. Planck also, on large angular scales and averaged over large regions of sky, measured a non-zero TB signal. That is the correlation between the total intensity and the B mode component of the dust, which is odd. Haha, little joke. It is a parity odd quantity, so it's a interesting thing to measure, especially averaged over so much of the sky at once. And my latest picture of what's going on here is that is originating from small misalignments between the projected magnetic field orientation and the direction of anisotropy of density structures in the dust. Okay, so think of it as a long axis of the filament in this little cartoon, right? You broadly get this positive TE signal from the fact that these things are mostly on average aligned over the sky. But any little misalignment of this signal will make the polarized emission from my little cartoon filament here have a non-zero TB signal, and the sign of that TB will depend on the handedness of this misalignment. And so this picture we can poke at by taking the difference in angle between our morphological map, which assumes perfect alignment between these density structures and the magnetic field orientation, and the actual measured magnetic field orientation. And we've found, I'm going to refer you to both these papers for the, I think, fascinating details, but we've found some reasons to believe this is what's going on in the ISM, and have ideas for what this picture predicts for example, an EB correlation in the dust polarization. Something to worry about if any of you are looking for isotropic cosmic birefringence, for example. And so now we have this framework, right, where we take some data, we built a model that turns it into maps of the dust polarization, or maps of the linear Stokes parameters based solely on the morphology of H1. And then we can compare it to actual measurements of the magnetic field or of the dust polarization in general. And there's potentially a lot to be learned here, as I mentioned earlier, from diving into what is the optimal mapping between this H1 morphology to polarization and why that's the case. So my graduate student, George Halal, is leading some excellent work on this. I'm excited to see where it goes. But we have an ability now to take, well, H1, but really any image you wish and turn it into a polarization map for you. So here's the Stanford logo expressed as an E-mode polarization field, in case that's something you were hoping to see today. And but this iterative comparative process, I think, is going to be really powerful for asking exactly these questions, right? What is it specifically in the ISM morphology that is most predictive of the dust polarization? You can also use this as a purely galactic signal to cross-correlate your dust polarization with. The H1 template is not contaminated by the CMB polarization, which is not the case, unfortunately, well, or fortunately, for all of the frequencies of data that we measure with experiments like bicep keck. So this was also led by my graduate student, George Halal. But he showed that you can use these templates in cross-correlation with your polarization from your CMB experiment to cleanly probe the aspects of the dust polarization in your field. Surely a lot more to be done there. We can also use the fact that we built these three-dimensional maps of the magnetic ISM structure. And this is a direction I'm really excited about for the future, in particular because we will have this survey called PASIFY that will increase by several orders of magnitude the sky density of starlight polarization measurements that we can get our hands on in the optical. The beauty of starlight polarization is that, especially now with Gaia, we have distances to the stars. And so we can actually bracket where along the line of sight that polarized signal is coming from. Gina Panapoulou has done this beautiful work with precursor data for PASIFY from an experiment called Robopol. Here she's cleverly picking two lines of sight, one that in the H1 emission intersects both a local velocity cloud and an intermediate velocity cloud, and then one adjacent sight line that basically just has an emission contribution from the local emission or the low velocity emission. And so by comparing the starlight polarization in these two regions, one can tomographically disentangle what the magnetic field structure is along the line of sight. And for our purposes, we can then compare the answer from starlight polarization, I don't know why that's happening, to what we pull out of our 3D H1 base maps by just grabbing the portion of our map that is at the velocity coincident with the cloud. And we find that these are very well aligned, which to me is extremely promising for the future of combining these types of H1 based local estimate, or maybe prior is a better way to think of it, of the local magnetic field orientation with these tomographically disentangled measurements of the starlight polarization. Also really excited about the work people like Joanna are doing with three-dimensional dust maps, because this is all eventually what we need to be putting into our model of the three-dimensional structure of both the density and the magnetic field. One more thing that we can do with this line of sight data, we also know that in just a general picture, if you have dust clouds along your line of sight with different dust SEDs, okay, that are also sitting in differently oriented magnetic fields. That should generically lead to a frequency dependence in the polarization angle that you measure in the dust emission, right? If you are a cosmologist, your reason to worry about this is that you might want to be taking a higher frequency channel of your data where the dust is better measured, with better signal to noise, and using that to infer the dust contribution at 90 or 150 gigahertz where your CME is brighter, right? And you should worry about the idea that there might be substantial decorrelation in the dust polarization between different frequencies. Here, we can look for this effect in current data, statistically in Planck data, by basically knowing where to look, by basically being able to select sight lines that have a high probability of having two different contributions from two different clouds, in our case, H1 clouds separated in velocity space, and in our case, sitting in different magnetic fields, meaning being separated in this orientation space that we measure in the H1. And so we can define a control set of sight lines that we think are as simple as possible, just dominated by one H1 cloud along the line of sight, and compare what we see to some target set of sight lines where we think this effect should be most severe. The worst case scenario, or the best place to look for this effect, is basically two clouds with similar contribution to the column density along your line of sight that our prescription would suspect are sitting in differently oriented magnetic fields. And then in the data, we can look at the angle difference of the polarization angle at two different frequencies in Planck data and compare the dispersion of that angle difference between our control and target populations. The upshot of this work, and I encourage you to dig in for the fun statistical details, is that we detect evidence for this sort of line of sight frequency decorrelation effect. And this is detected basically statistically over large areas of sky in current data. But of course, you could imagine doing better and better as our data improve, and also as we extend our high frequency lever arm, perhaps. This is also just to show you that dispersion on aggregate also finds a trend with the angle difference in the H1 data of the two clouds that we select along the line of sight, which is pretty neat. Okay, and I want to tell you with my remaining minutes here about how we can use this morphological information to also probe questions about the phase structure of the ISM. This, I think, is a fascinating question for understanding the magnetic field, as well as just for understanding basic ISM physics of how it is that gas is transitioning between different physical states. Your own Jessica Campbell did some absolutely beautiful work comparing different tracers of both the gas emission and the magnetic field in different phases of the ISM. Here, my graduate student, Minji Lei, has done some fantastic work focused on the two phases of the neutral gas that we are probing in H1. So this is the warm neutral medium and the cold neutral medium are the two thermally bistable states of the ISM at constant pressure. And so the H1 is in general distributed into those two stable states, and some fraction of the H1 is in some thermally unstable state in between them as well. And the most direct way to get a handle on the thermodynamic state of that gas is to have absorption line measurements in addition to emission measurements of the H1, so that you can make direct constraints of the spin temperature and the optical depth. That requires that you have some bright background radio source toward which you can get your absorption line measurement. And so there has been a long history really of people wishing to sidestep that and instead try to use purely the H1 emission to partition that emission into phases of the ISM. And that's normally done entirely in the spectral domain. And so you take your H1 line and you fit a bunch of Gaussians to it. Antoine Marchal, when he was here, wrote one of the latest and greatest algorithms to try to do that in a regularized way, to decompose the emission of H1 into different phases. We wanted to ask whether there is information on the phase structure of the H1 encoded in the H1 morphology, the theme of my talk. And to address this question, we used an algorithm called the wavelet scattering transform, which is gaining some popularity and has definitely made its way into a few different subfields. I know a few people here have worked with this in cosmological contexts. The basic idea is, when applied to image space data, is that you are making successive series of convolutions with wavelets at different scales and different orientations, and then taking a modulus. That at first order here gives you a set of coefficients that are correspond to each of the wavelet scales that you have applied in your convolution. And then you can do that again in order to create another set of coefficients that probes these scale and orientation interactions between your data. And so if this basic architecture looks sort of reminiscent to you of a convolutional neural net, that was actually some of the initial motivation of setting up this mathematical framework, was to study what it is that neural nets are doing inside the box, but in a way that is completely predictive. For our purposes, that means that this is a way of quantifying morphological information very generically, right? We're not predetermining that we're going to look at linear structures or anything like that. We're instead just collapsing this spatial information into some set of coefficients that we can play with. And unlike a convolutional neural net, there's no training step going on or anything like that, where you're just making a statistical description of the data. And then we are putting those coefficients into different, more compact descriptors that we think are interpretable in some way. And so, for example, we can look at the set of coefficients that probes the wavelet scattering transform coefficient of two different scales at orientations that are parallel to one another in those two scales versus orientations that are perpendicular to one another of those two scales. And here we're taking some image of H1 emission, some region of sky, and making synthetic images where we crank up that orthogonally oriented coefficient S perpendicular, or that parallel coefficient S parallel, just to give you a visual idea of what these are probing, right? So in the language of linear filamentary structures in the ISM, S parallel is probing more of that linear filamentary structure. The more diffuse blobby stuff will have higher S perpendicular coefficient. And so our approach here is to compute these coefficients over a bunch of little patches of the sky toward which we have absorption line measurements and a sort of ground truth measurement of the CNM mass fraction from that. And the takeaway is that we've found that this H1 morphology is correlated with the measured FCNM fraction, with the measured CNM fraction, and in an interpretable way. So I realize that this is a big matrix that is showing you these correlations of these different coefficients. So on the bottom, this is showing you pairs of scales in the scattering transform. And on the y-axis, this is showing you the different mutual orientations. What you should take away from this is that the more parallel oriented regions of this correlation plot are positively correlated with the measured CNM fraction from these absorption data. And the more orthogonally oriented coefficients are actually anti-correlated with those data. This is not the only way to compactify our data, but this is one that we felt we had some interpretability behind. This is another way to see that this result, that this morphology is correlated with the CNM fraction, is to look at the ratio of the far infrared emission to the total H1 column as a function of what you have measured in these coefficients for your sightline. And the takeaway again is that we see this as you move to higher S-parallel coefficient, as you find morphological regions that are better described by stringy features in your H1 emission at the velocity coincident with the absorption, with the absorber, you see this ratio, you see the far infrared to NH1 ratio increase. And conversely, you see it decrease as you move to regions that are better described by this metric that is more sensitive to blobby diffuse structure. So this is in press, I suppose, at AppJ and on the archive now. I encourage you to check it out and to watch this space because we are up to some cool things. Please.
I sort of feel like it's a good folder to me and was really small features.
Yes.
Can you say anything about that in this analysis?
Yes, I absolutely agree with that statement. And in fact, since I have a few minutes, I think that we see evidence of that in a number of different ways. One is that if you take regions of H1 emission in narrow channel maps and you just filter the data to filter out large scale information, right? You also see this increase of the far infrared to H1 column. And that, of course, can in general be coming from a few different things, right? You can either be increasing your numerator or decreasing your denominator, and it's not necessarily CNM as opposed to molecular gas, but this is for very diffuse high galactic latitude data, where this is at least consistent with this being CNM. And this is the reason, this is what is driving this magnetic alignment that we see between the channel map intensity structures in H1 and the magnetic field. That is important to say because there has been a different view in some literature that would claim that instead what you're seeing in the narrow channel map of H1 emission is actually uncorrelated with the density structure and instead just imprinted by the turbulent velocity field, basically moving intensity into or out of. This is Alex Lazarian's velocity caustic picture, but that is testable and wrong. This is driven, the fact that these things are magnetically aligned is really driven, it turns out, by these preferentially cold CNM structures, yeah, which are preferentially small scale. See this in a lot of other different too. And I am happy to stay here for the next hour and tell you all about all of the evidence for that. Yes.
Does that mean that if you were to make a map of H1 in the broader WNN lines, that you wouldn't see as strong of a correlation between orientation and polarization?
Yes, and that is exactly what you see. So for example, if you just take the total H1 column, right, where it's the WNN that's dominating that, you decrease your correlation with the magnetic field. Exactly. Yeah. Also a reason to do this in the H1 to begin with, as opposed to just taking a dust map, right? In addition to it giving us interesting three-dimensional information. Yeah, that's a great question. Yeah, wait. Yeah, absolutely.
Most of it talking about orientation. Do you have any way to track the magnitude of that?
From this type of approach, the only way to do that is the traditional thing to do is to use something like the Davis-Chandrasekhar Fermi method, right? And make a statistical estimate of what you think the field strength is under these very strong assumptions that basically relate to the disorder in the field. Yeah. So, you know, there's nothing stopping you from using H1 orientation instead of starlight polarization or polarized the polarization angle of dust to do exactly that. But it has all the same caveats that Davis-Chandrasekhar Fermi has in general. I really think that there is a future here that we should all be striving toward of combining these data, combining the statistical information that we can get with that sort of analysis with direct measurements of the line of sight magnetic field strength from Zeeman splitting. Yeah.
You haven't mentioned Zeeman at all.
Yeah. We are working on that. My graduate student Martin Nwatka is working on that, and that is, I think, I mean, there are two things, right? That is the way to eventually more directly probe the three-dimensional magnetic field structure, and also the total magnetic field strength, because all you directly get from the Zeeman information is the line of sight. It's a hard problem, and we don't have nearly enough Zeeman measurement. That's really limiting for this work. And so if you go out into the world and yeah.
Have a telescope that dedicates a lot of time to Zeeman and stuff that falls down.
Yeah, I'm aware of that. It is a very tragic history. Yeah. Yeah, I mean, Arecibo taught us most of what we know about the field strength in the CNM and all of the regions that I'm talking about here, right? And a huge amount of what we have inferred about the role of magnetic fields in star formation is all anchored to these statistically very few measurements. I mean, this is a place that I think we as a field need to push, because we have this technique. We need the telescopes and the telescope time and the excellent, rigorous control of our polarization systematics and the willpower. But yeah, that would be great. My postdoc Marnoosh Tahani has also done some really fascinating work with rotation measure information toward molecular clouds, where the idea there, the challenge with the rotation measure is that you're seeing everything along the line of sight. But her trick is to use a sort of on-off technique where you can get rotation measure attributed to the cloud as opposed to rotation measure attributed to everything else along the line of sight by comparing on to off. And then if you also are modeling the thermal electron distribution in your cloud, you can use that to constrain the three-dimensional geometry. Well, you can use that to get the line of sight component of the magnetic field and combine that with these sort of dust polarization tracers to constrain the three-dimensional magnetic field orientation molecular clouds. So really, I think, you know, the trick here is to use everything we can get our hands on, but that requires us really building up these tools of how we can use these different tracers in new creative ways, which is a good way for me to summarize this, and then I'm very happy to keep answering questions. So my takeaways here are that there's just a huge amount of physical information encoded in our observations of the ISM that we should be using. We just need to get creative and come up with these techniques. H1 morphology in particular has been super fruitful so far, and I'm really excited to see what we find next to probe the magnetic field structure and to probe even the phase structure of the ISM just purely from the emission. Which, by the way, means that the best possible way to phase decompose those data must involve using both the spatial and spectral information. And so that's where we'd like to go next. the better we can do all of this, the better we can clear the way for cosmological discovery. And so we've really built up a partnership with CMB experiments that I collaborate on, both to do this galactic science and to understand this polarized dust foreground better. And this is now being built up at Stanford as my research program as a new PI there. And so I encourage you all to stay in touch and stay tuned. Thank you.
Thank you so much. I think I'm gonna pause the recording now.